it is now time for us to take a quick look at gas-forming reactions. So any reaction that produces a gas qualifies as gas-forming. So they can actually be combination, decomposition, substitution, or exchange reactions. So in order to know if a reaction forms a gas, you kind of need to know certain gases. You have to be able to recognize the following molecules: H2, N2, O2, NH3, CO2, H2S, and SO2 as being gases at room temperature, 1 atmosphere of pressure. Okay, so we have seen some gas-forming reactions in previous lessons in this unit. So we saw a combination reaction that's a gas-forming reaction, the reaction of sulfur with oxygen to give sulfur dioxide, one of the gases on the list. We've seen numerous decomposition reactions that are gas-forming. So for example, calcium carbonate decomposing to give calcium oxide and CO2, mercury oxide giving off oxygen, sodium azide giving off nitrogen, and sodium chlorate giving off oxygen, all in the decomposition lesson. And then we have seen some substitution reactions, in which case metals react with either water or acid to give off hydrogen gas. Okay, so the other gases on the list, we've already seen CO2, but NH3, CO2, and H2S can all be generated by acid-base reactions, which we are treating as a sort of exchange reaction. So let's start by talking about a reaction that generates ammonia, NH3, and that is simply the reaction of an ammonium salt with base. Okay, so in this case, we're going to start with ammonium nitrate, so this is your molecular equation, plus NaOH is going to generate sodium nitrate, aqueous, plus NH3 gas plus water liquid. Okay, how does this work? Well, to answer that question, let's write the ionic equation. So if we take ammonium nitrate, split it up into NH4 plus and NO3 minus, take NaOH, split it up into Na plus, OH minus, and then on the right side, we've got an Na plus, an NO3 minus, NH3 gas, and H2O liquid. Remember that liquids and gases don't get broken up into ions, just compounds that are aqueous. Okay, and now if we cross out the spectator ions and leave the net ionic equation, what we have is NH4 plus being an acid, OH minus being a base. The proton is transferred from the acid to the base, and that makes NH3 and H2O, NH3 being a gas and H2O being a liquid. Okay, so this is an example of an acid-base reaction that forms a gas as one of the products. Okay, next reaction I want to consider is the generation of hydrogen sulfide from reaction of a metal sulfide with acid. So in this case, we're going to look at sodium sulfide reacted with hydrochloric acid, and that's going to generate sodium chloride in solution and H2S gas. So skipping down to the net ionic equation for this, this is going to be S2 minus, that's what Na2S is going to turn into, plus 2H plus, giving you H2S. Okay, so you can see that you have a base, an acid coming together. It's the same similar net ionic equation to that of a strong acid and a strong base. Okay, so H2S, we can generate it all we want on paper. We probably don't want to generate very much of it in the lab for the reason that it smells like rotten eggs. So again, this reaction is similar to the reaction that we saw in a previous lesson of copper oxide with acid. And then since sulfur is directly below oxygen on the periodic table, the reactivity of sulfur compounds should be similar to the reactivity of oxygen compounds. Now, sodium sulfide is going to be a little less reactive than sodium oxide. Remember, sodium oxide will react vigorously with water. For sodium sulfide, for this reaction to go, we want to add acid to it because simply sulfide is not quite as strong of a base as oxide is. All right, the final example of gas-forming reactions via exchange that I want to cover are reactions that generate carbon dioxide. So these are actually quite important reactions. And in both of the cases we're going to look at the reaction of a carbonate or bicarbonate salt with acid. So for our first example, we're going to look at sodium carbonate. Okay, remember from your polyatomic ions that carbonate is CO3 2 minus, bicarbonate is HCO3 minus. So sodium carbonate plus 2 HCl's is going to give you sodium chloride in solution plus CO2 gas and H2O liquid. Okay, so how does this work? Well, the acid-base reaction that's going on here, okay, this is the net ionic equation for the acid-base reaction. I'm not going to go over writing the full ionic equation again, but the net ionic equation is CO3 2 minus, your base, plus 2H plus, your acid, giving you H2CO3. So we're taking 2 protons and transferring them to the base. Now this H2CO3 in aqueous solution is actually unstable because in aqueous solution it undergoes a decomposition reaction to give carbon dioxide gas and water liquid. Okay, the next example that I want to look at is what we call the traditional volcano reaction, which I'm sure you've seen at some time, which can be done under household conditions by reacting baking soda and vinegar. So baking soda is simply another name for sodium bicarbonate, which, as I've said before, is NaHCO3. And then vinegar's active ingredient is acetic acid. So it's going to be, vinegar is usually a 5% aqueous solution of acetic acid. And for the purposes of this equation, I'm using the HC2H3O2 formula for acetic acid. So if we do an acid-base reaction, we're going to transfer proton from the acid to the base. Okay, so instead of HCO3 minus, that's going to become H2CO3. And then the acetic acid now exists as its conjugate base. Okay, so this is a weak acid reacting with a weak base. So it's going to exist as its conjugate base, so therefore it gets the sodium associated with it in a molecular formula. Okay, so here's the ionic equation for the acid-base reaction. And then the decomposition reaction is identical to the decomposition reaction we saw for carbonate because we have made carbonic acid, H2CO3, and it's going to decompose in solution to give CO2 and H2O. Okay, one last example, and that's the chemistry that's actually involved in cave formation. Okay, so you know that caves are open spaces that exist underground in the middle of, what may have once been, well, what was once solid rock. So in order to be able to form caves, the rock that exists has to be limestone. And limestone has the chemical formula calcium carbonate. So if calcium carbonate is treated with acid, that's what you see in the picture here. If you, in this case, take hydrochloric acid and put it onto a piece of limestone of calcium carbonate, you can see that it starts to bubble. Okay, and that's actually the carbon dioxide that's being given off in this reaction. So in natural sources, we're not actually generating HCl, but we all know that there is acidity in our rainwater. Not going to get into the details of exactly what acids are reacting, but I'm just going to put into this equation H+. So that acidic rainwater seeps into the ground and eventually makes its way down, in some cases, if the landscape is right, to a limestone layer. And if it does, it's going to undergo this reaction. The calcium carbonate gets broken down into an aqueous solution of calcium 2+. Okay, because what happens is that you are protonating the carbonates, so then the calcium carbonate can dissociate. You can get calcium 2+, that's soluble, of course. The H2CO3 then decomposes into CO2 gas and H2O liquid. So initially, caves, as soon as they're formed, are filled with carbon dioxide. They wouldn't exactly sustain life as we know it, but once a cave gets opened up to the air, to the atmosphere, then you can, of course, get gas exchange between the gas that was originally in the cave and what's out in the air. Okay, so those are our gas-forming reactions. And then in our final lesson in this unit, we will discuss oxidation reduction or redox reactions.